In the last video, we learned how to decrease an error function by walking along the negative of its gradient. Now in this video, we're going to learn formulas for these error functions. The two most common error functions for linear regression are the mean absolute error and the mean squared error. First, we'll learn the mean absolute error. So here's our point and our line. The point has coordinates x, y, and the line is called y hat since it's the prediction. So our prediction for this point is going to be the point in the line with the same x coordinate as our point, that is the point x, y hat. This means the vertical distance from the point to the line is y minus y hat, and that's what we'll be calling the error. Notice that this is not the actual distance to the line since this would be a perpendicular segment, but is the vertical distance from the point to the line, which is the distance between the point and its prediction. Now our total error is going to be the sum of all these distances for all the points in our data set. And sometimes we'll use this as our error. But in this case, we'll use the average or the mean absolute error, which is the sum of all the errors divided by m, the number of points in our data set. Using the sum or the average won't change our algorithm since it would only scale our error by a constant, namely m. And notice something here, which is that we have an absolute value around the y minus y hat. The reason is that if the point is on top of the line, the distance is y minus y hat, but if it's under the line, then it's y hat minus y. We want the error to always be positive, otherwise negative errors will cancel with positive errors. Therefore, we take the absolute value of y minus y hat. So our mean absolute error is the average of all absolute errors, or in other words, the sum of all these absolute values divided by the number of points, which is m. We're going to plot this error over here in a graph. Obviously, as we mentioned before, the graph has more dimensions, but this is a two-dimensional simplification of that graph. And as we descend in this graph using gradient descent, we get a better and better line until we find the best possible fit with the smallest possible mean absolute error.